Hello, Hilary. How are you?
Hi, I'm good. How are you?
I'm fine, thank you. Now you're separate?
Yes.
Hi.
I am not at home today.
Okay, that's okay. So, any questions?
No.
No.
All right. So, okay. So I started recording. Yeah, I started recording. So it's time. So, any comments? Any questions, Agnes?
No, I don't have any.
Okay, great. So I'm going to show you where we are in the syllabus, and I'm going to share my screen with you. Let's see if I can. All right. So am I sharing my screen now?
Yes, you are.
Oh, yeah, okay, thank you very much. Okay, so we covered already the first topic, the second, existence of solutions, which is Weierstrass theorem. We also covered unconstrained optima. So basically we saw the first and second order conditions. And now we are in topic number 5, which are equality constraints in the theorem of Lagrange. And this is the objective. At the end of this topic, the students will apply Lagrange's theorem on constraint optimization problems when the constraints are identities. And we are going to spend 2 weeks on this topic. So this will be week 6 and week number 7, if everything is correct. And those are the topics we're going to cover. So we're going to cover constraint optimization problems, equality constraints and the theorem of Lagrange, second order conditions using the theorem of Lagrange, 2 examples from economics, and then we're going to prove the theorem of Lagrange and the second order conditions. Now, before I start, remember that we saw first order and second order conditions here. First order conditions provided necessary conditions for some point to be the optimum of a problem, and second order conditions provided sufficient conditions. Well, same thing will happen in the next topics. So we're going to see, for instance, the Lagrange's theorem, which will provide necessary conditions for one point to be the optimum, and the second order conditions will provide sufficient conditions. Okay, so you can see that we're going to see the same things over and over in the following topics. Okay, and that's the basic idea. Okay, any questions on us where we are right now?
No.
No? Okay. So let me see. Okay. So let's start the class, the lecture. So we are going to talk about topic number 5, equality constraints and Lagrange's theorem. And I'm sure that at some point you saw Lagrange's theorem. But okay, so we are going to give an introduction. So the introduction will be as a remark. Okay, so in general, suppose that U is a subset of Rn, which is open. And we have various functions. So we have function G that goes from Rn into Rk, a function H that goes from Rn into RL, where the functions are given component-wise. And those are the components. We consider a feasible region of the following form. So it's a set D, I'm going to call it D, which is U intersected with those vectors satisfying at the same time the g of x is equal to 0 and h of x is greater than or equal to 0. The most general optimization problems that we are going to consider are the following. So this is not problems. One type of problem is to maximize the function f of x over the feasible region D. And the other would be a minimization problem, okay? Now let's talk first about the maximization problem. Okay, in notation, this can be written equivalently in the following form. So the problem is to maximize the function f of x such that the following conditions are satisfied. G of x is equal to 0, h of x is greater than or equal to 0, and x is in D. I'm sorry, x is in U. Okay, these are the type of problems that we would like to solve. This is the most general form of those problems. This is what we call the objective function. And these are what we call the constraints.
So it's very similar to the problems we solved last year, right?
That's right. That's right. So, and in general, you see, you can have identity constraints or inequality constraints, and it's not the same kind of techniques that work for both conditions. Okay. But this is what we would like to do ultimately, solve these type of problems. Of course, you can also have minimization problems. Alternatively, we would like to solve these kind of problems, minimize the function f of x when x is in D. And this can be rewritten also in equivalent form. Okay, this problem can be expressed in this way. So minimize the function f of x such that f g of x is equal to 0, h of x is greater than or equal to 0, and x is in u. Okay, can we change the page?
Yeah.
Okay, thank you. Yes, okay. So here the conditions g of x equal to 0, these are called equality constraints. And these conditions on the previous page are called inequality constraints. Now, here I'd like to remind you, notice that h is a vector function. So if we go back, we're going to notice that h has components h1, h2, so on, hl. In this case, h of x greater than or equal to 0. This notation means the following, means that h1 of x is greater than or equal to 0, h2 of x greater than or equal to 0, and so on, right? HL of x is greater than or equal to 0. I think some time ago we introduced this notation, right? So something important, I mean, notice that every inequality constraints can be rewritten in this form. So that's what I'm going to observe now. So this is a small note. So any other inequality constraints? Can be rewritten in the following form. And this is obvious, right? Because, for instance, if you have h1 prime of x is greater than or equal to h2 prime of x, or h1 double, I'm sorry, h1 double prime. Well, this is equivalently rewritten as h1 of x minus h1 prime double prime of x greater than or equal to 0. And you can just call this expression h1 of x. So equivalently, you obtain this inequality, right? And this is essentially what we did in operations research last semester when we wanted to have inequality constraints of that form. And I'm sure you remember that.
Yes.
Yes. Okay, great. Thank you. Let's consider one of those examples from economics that we saw before. So I'm going to remember the utility maximization problem, and I'm going to notice that that problem can be rewritten in this general form. So more precisely, it'll be a maximization problem which can be rewritten in this form. Okay. So this is an example. Okay, so let's remember that problem. So in this problem, the feasible region was a set of this form. So it was, remember we used this notation. It was a set that depended on two parameters, P and I. And it was the collection of all X in R plus N with the property that P times X is less than or equal to I. So here there are various constraints, as you can see. The vector X, the vectors X, need to have non-negative components, and this inequality must be satisfied. Okay. So we are going to consider n+1 constraints. So we're going to define the functions hi, or I'm sorry, hj from Rn into R. They're going to be given in the following form. Okay. Hj is going to, I'm sorry, of X is going to be xj. Where X is this vector. And that's for j from 1 to n. So what we would like to do is to make hj greater than or equal to 0 in order to satisfy this condition, right? So that X is in this set. But we still need to consider this other condition. So I'm going to define another function on the next page as soon as you finish, ladies.
I'm ready.
You're ready? Okay. Okay, thank you. So, and we are going to have hm plus 1 of x equal to, what was that? So that'll be I minus p times x. And then you define the function h as the function whose components are h1, h2, so on, hm plus 1. So you see, this is going to be a function that goes from Rn into Rn plus 1. And in that way, then the feasible region is the collection of all x in Rn with the property that h of x is greater than or equal to 0. And now you can rewrite the utility maximization problem, right? The problem is then to maximize some utility such that h of x is greater than or equal to 0 and x is in Rn. Okay. Which is an inequality constraint problem, right? And essentially every problem that we have seen can be rewritten in this form. So it'll be to maximize or minimize some function subject to equality constraints or inequality constraints. Well, this leads us to induce some classification optimization problems. And I'm going to talk about that in the following remark. So this is on the classification of optimization problems. Okay, so some problems are what we called unconstrained problems. And these are problems of this form, so they are just maximize or minimize some function f of x when x is in some set U. So they're unconstrained because there are no additional constraints. We also have equality constraint problems. Which are problems of this form. So you want to maximize or minimize some function such that the following conditions are satisfied. G of x is equal to 0 and x is in U. We have also inequality constraint problems. Which are of the following form. So you maximize or minimize f of x. The conditions are of the form h of x must be greater than or equal to 0 and x is in U. Okay, did you finish, ladies?
Yes.
Yes, okay.
Yeah.
Okay, so and the last type of problems in optimization are a mixture of these last two problems. And I'm going to mention that on the next page. So they are what we call exactly mixed problems. Which are problems of the form maximize or minimize a function f of x. And the conditions are g of x is equal to 0, h of x greater than or equal to 0, and x is in U. Okay. Very well. So in this topic, we are going to be talking about the second type of problems, equality constraint problems. And I'm going to try to introduce Lagrange's theorem, which is the most important tool to try to solve those problems. Now to that end, I'm going to introduce some notation. And that'll be in the following remark. Okay, so let A be any matrix. Remember that the rank of A well, this is going to be a number. It's going to be represented by row of A. So this is the rank of A, and that's the maximum number of linearly independent columns of the matrix A. Which is the same thing as the maximum number of linearly independent rows of A. Okay, so this concept is going to appear in Lagrange's theorem, and that's why I am remembering this concept here. And you know, to determine the rank of A, you can use various techniques. One of them, for instance, is based on elementary operations on rows and columns. A process very similar to Gaussian elimination. Okay. So this is nothing new. And the following remark isn't new either. So suppose that you have a function. So this function goes, let's say, from Rn into Rp. And suppose that this function is differentiable at some point. So suppose that f is differentiable at some point x in Rn. And additionally, suppose that this function is given component-wise as f1, so on, fp. Then the derivative of this function is going to be a matrix, right? So it'll be the partial of f1 with respect to x1 at x, the partial of f1 with respect to x2 at x, and so on. Okay, in the next row, you have all the partials of f2. You keep going, and finally, you have the partial of fp. Okay, so that's a derivative, right? Okay, so I'm going to use both concepts. And finally, we should probably mention explicitly that Lagrange's theorem is used for solving equality constraint problems. So this theorem is actually the most important tool to solve that kind of problems. And we are going to introduce that theorem on the next page as soon as you finish copying.
I'm ready.
Okay, thank you. Thank you. All right, so I'm going to change the page. And Lagrange's theorem is the following result. Okay, as usual, the objective function is going to be a function that goes from Rn into R. And we are going to have constraints, identity constraints, which are going to be summarized by the function g. It'll be a function that goes from Rn into Rk. And you suppose that these functions f and g are of class C1 over Rn. Okay, let x star be a local maximum or local minimum for the function f on the following set, on the set D, which is U intersected with this region. Here, U is an open set. And for the sake of clarity, remember that G is given component-wise as G1, so on, GK. Okay, those are hypotheses, and this is also hypothesis. So we are going to suppose that the rank of this matrix, I'm sorry, it's not F, it's G. The derivative of G at X star is equal to K. Under all of these hypotheses, there is a vector which I'm going to call lambda star, whose components are going to be lambda 1 star, so on, lambda k star in Rk. with the property that the derivative of f at x star plus the sum of lambda I star from I equal 1 to k of the derivative of gi x star, that's equal to 0. This is Lagrange's theorem, and it's very likely that you saw it in the vector calculus at some point. Possibly you also saw the proof, but we are going to see the proof also here in this course. Now let's examine this theorem. First of all, look at the following. So the theorem states that if x is a local maximum or local minimum for the function f, then something happens. This means that Lagrange's theorem provides only necessary condition for some point to be a local maximum or local minimum. Okay, and I'm going to mention that. So Lagrange's theorem provides necessary conditions for some vector in Rn to be a local maximum or a local minimum. So what's the idea behind the Lagrange's theorem from the operational point of view? You see, you find all the x's, all the x stars, for which there is some lambda satisfying this property. And you hope that there is only finitely many points with that property. Those points are going to be candidates to be local maxima or local minima of the function. That's the idea, okay? Exactly as when you use the first order conditions. Remember, the first order conditions tells you that critical points for a function are candidates to be local maxima or local minima. It's the same idea in this case. Another important observation is that this theorem is for equality constraint problems. Okay. So let's mention that. So this theorem is for equality constraint problems. And finally, one last remark. These constants have a name in the context of Lagrange's theorem. That's what they call the Lagrange multipliers, right? So the constants lambda 1 star, lambda 2 star, lambda k star are called Lagrange's multipliers. Okay. Any questions?
No.
No. Okay. And possibly you saw this theorem before, right?
I think so, yes.
Okay, great. Okay. I'm going to provide one example. Okay, so keep this in mind. Can I change the page? Yep.
I am finished.
Okay, thank you. So let's saw one example. Let's see one example, sorry. In this example, we're going to consider the following function. So we are going to maximize the function x cubed plus y cubed. And we are going to consider the following restriction: x minus y is equal to 0 and x comma y is in R2. Do you notice that this is an equality constraint problem? Constrained. And in our notation, so the function f of x comma y in this case will be x cubed plus y cubed, and g of x comma y is x minus y. Okay. So we're going to use Lagrange's theorem. So Lagrange tells you that if this point is a solution for this problem, so in other words, it's a local maximum, let's call this problem star. Then in that case, there is some Lagrange multiplier lambda star in R with the property that the derivative of f plus lambda star times the derivative of g that's equal to 0. Okay. So we need to calculate these derivatives. And let's do it. What's the derivative of f in this case? So there'll be the partial with respect to x, that's 3x squared, comma the partial with respect to y, that'll be 3y squared. And we can also calculate the derivative of g. So the derivative of g is 1 comma negative 1, right? Okay. So we substitute into 1. So you have this vector plus lambda star times this other vector. That's equal to 0. And this is equivalent to the following. So you have this system of equations, 3x squared plus lambda star. That's equal to 0, 3y squared minus lambda star. That's equal to 0. And finally, you remember that there is this constraint, right? X minus y is equal to 0. And this is the basic idea about Lagrange's theorem that an optimization problem becomes an algebraic problem. So at the end, you need to solve a system of equations. In most of the cases, this system of equations is going to be complicated. But you hoped to get the solution, right, somehow. Okay. Let's proceed now to solve this system of equations. I'm going to call these equations number 2, number 3, and number 4. To start with, note that from equation number 4, you obtain that x is equal to y. And I'm going to use equations number 2 and number 3. Okay, so please let me know when you finish.
I am ready.
Okay, thank you. Okay, so instead of y, I'm going to write down x. So let's see. So you have 3x squared plus lambda star is equal to 0. And 3x squared minus lambda star, that's equal to 0. So you add these two equations and you obtain that 6x squared, that's equal to 0, right? Which implies that the critical x component that's equal to 0. And then you remember that y was equal to x. And you can also obtain the value of lambda star from here. For instance, from the first one, lambda star is equal to minus 3 x star squared, which is equal to 0. And the conclusion is the following. So you conclude that if x star, comma y star solves the problem, which was, I think I called it star, right? So if this is a solution for our initial problem, then x star, comma y star must be the origin. Okay. Any questions so far?
No.
So, okay, now there is something I'd like to point out, but before that, Eva and Agnes, did you catch up?
Yeah.
Okay, great. Very good. So there is something that we are missing here. Okay, this is an application of Lagrange's theorem, and we reached this conclusion, but we skipped one assumption. And this is what they usually do, most of the cases, especially people in engineering, not mathematicians. You see, when you go back to Lagrange's theorem, indeed, so you see that if x star is a local maximum or minimum for the function f satisfying this condition, then there must exist some lambda that such that this happens. Okay, everything was okay, except that we forgot to check that this condition is satisfied. Okay. And that's something I wanted to talk about. This is especially important, and we are going to see in when we see the proof of Lagrange's theorem that we need this condition for Lagrange's theorem to be satisfied. Also, we can check that with counterexamples. So I'm going to mention this. So this is like a note. So here we forgot to check that the rank of the derivative of g at x star, comma y star, this is equal to k. And this is with exclamation mark. This is not a factorial, okay? But this condition is actually satisfied in this case. So I'm going to mention this. It is satisfied. Why is that? So we remember that the function g function g has the form x minus y, right? And what's the value of k in this case? What is k? K is the number of equality constraints, you see? And in this case, k is equal to 1. Okay, so let's obtain the derivative of g. We obtained it before, right? So the derivative of g at x comma y is 1 comma negative 1. We evaluate the derivative at x star comma y star. So we have to do it, right? No problem, because this is a constant vector. That's still 1 comma negative 1. And then you calculate the rank of this matrix. Then you remember what the rank is. The rank is the maximum number of linearly independent columns, which, as you can see in this case, that's equal to 1. So this means that this condition is satisfied. And that tells you that the application of Lagrange's theorem was correct. So we applied correctly Lagrange's theorem. Okay. Okay. I'm going to see a counterexample. But before that, a remark. Did you finish, ladies? Should I wait for you?
Yes.
Finished.
You finished? Okay.
Me too.
You too. Okay, very good. So okay, so I'm going to mention this. The condition, the rank of the derivative of g at x star equal to k must be satisfied for the conclusion of Lagrange's theorem to hold. And we are going to illustrate this with the following example. So see the next example. So in the next example, I'm going to consider a particular case in which this condition is not satisfied and the conclusion of the theorem doesn't hold. Okay. So we're going to consider the following problem. So we are going to maximize this function minus y such that the following holds is y cubed minus x squared that's equal to 0. And x comma y is in R2. I'm going to call this problem problem star. Oops, sorry. Okay. Are you ready?
Yeah.
Okay. Okay, let's start to identify things here first. So in this case, the function f of x comma y is equal to minus y. And the equality constraint is y cubed minus x squared, right? Okay, now let's observe the following. So this inequality, okay, so it's written g of x comma y is equal to 0. This happens if and only if y cubed is equal to x squared, which is always greater than or equal to 0. And that implies that y must be greater than or equal to 0. Are you with me?
Yeah.
Okay, pretty good. Okay, on the other hand, moreover, so if this is satisfied, if y cubed is equal to x squared, then y is equal to 0 if and only if x is equal to 0. I'm going to use this fact. I'm going to come back to it in a minute. In the meantime, recall that f of x comma y is equal to minus y. And because of this, okay, since you have that y must be greater than or equal to 0, then f of x comma y is going to be less than or equal to 0. And you have that it's equal to 0 if and only if y is equal to 0, in which case also x is equal to 0, according to this, right? So you see, the only solution for this problem will be actually the origin. That's when this function is going to be maximized and the constraint is going to be satisfied. So that's what I'm going to mention on the next page. Can we change the page?
Yes.
Okay. Okay. So as a consequence, the only solution for the problem star is the point x star, comma y star equal to 0, comma 0. Okay. That's a solution. And you notice that in order to obtain the solution, we didn't use Lagrange's theorem. Okay, so let's try to use now Lagrange's theorem. So I'm going to mention that. Let's use Lagrange now. So I'm going to remember g of x comma y. What was that? That was y cubed minus x squared. Okay, so let me calculate the derivative of g. So the derivative will be minus 2x comma 3y squared. And when you evaluate this derivative at this critical point that we know it's the maximum for the function, for the problem. So you see, this is derivative of g at the origin, which is going to give you the 0 vector. And you can tell me what the rank of this matrix is. The rank is equal to 0, right? And then you remember who k is. Remember, k is the number of equality constraints, which is equal to 1. Okay. So it's not true that this condition is satisfied. Okay. Now, what happens with the conclusion? Okay, so we know that this condition is not satisfied, but maybe there is some lambda, so there is a Lagrange multiplier satisfying the conclusion. That's the question. What happens with the conclusion of Lagrange's theorem? Okay, so in fact, we're going to check now that there is no lambda star in R, such that the following is satisfied. The derivative of f x star comma y star plus lambda star times the derivative of g x star comma y star, that's equal to 0. This doesn't hold. Okay, let's check that. Okay, let's move on. So let me remember who the function f is. The function f is minus y. So okay, we need to calculate this derivative. So the derivative of f at x star comma y, I'm sorry, first of all at x comma y. So that'll be 0 comma negative 1, right? And when you evaluate at the critical point, then that's still 0 comma negative 1. Okay, please let me know when you finish.
I have finished.
Okay, thank you. All right. Let's start to calculate the left-hand side of this equation. Okay, so I'm going to substitute. The first is 0 comma negative 1. Is that right? Yeah. Plus lambda star times the derivative of g, and that'll be 0, 0. You simplify. And you obtain this vector. Which is never going to be equal to 0. So for any lambda star that you take in the real numbers, this term is never going to be equal to 0. And as a conclusion, and as a consequence, the conclusion in Lagrange's theorem is never going to be satisfied. What's the moral of this example? So what we have learned is that if this condition is not satisfied, so if the rank of the derivative of g at x star, comma y star is not equal to k, then it's not necessarily true that there is some lambda star in Rk with the property that the derivative of f at the critical point. Okay, so this is in general, right? So I'm sorry. Plus the sum of lambda I star derivative gi x star is equal to 0. So it's not necessarily true that this conclusion is going to be satisfied. Okay. So you need to be really careful in this case. So that condition, the rank condition on this matrix, must be satisfied in order to exist the vector lambda with Lagrange multipliers. Okay. And as I mentioned before, this is going to be a hypothesis, a very important hypothesis in the proof for this theorem. And we're going to see that later on. Okay, so I think that'll be next week at some point. Before I dismiss you, I'd like to remember some definition. This will be a quick definition. Actually, it's not definition. This is a property that we were going to use later on. And I'm going to consider this as a remark. So suppose that you have a square matrix. Let A be a matrix of size n by n. Okay. And suppose that the rank is equal to n. Then we say that the matrix is non-singular. Or equivalently, we say that A is invertible. Actually, this is a property, right? So this is an if and only if condition. So A is invertible. if and only if the rank of the matrix is equal to n, right? So let me write it down. So in fact, we have that the rank of A is equal to n. Okay, I'm sorry. If A is an n by n matrix over the real numbers, then the rank of A is equal to n if and only if the inverse exists. Okay. So what we are going to do in the following days is we are going to use Lagrange's theorem to solve problems. Some of them are going to be mathematical problems, others are going to be problems from economics. Do you have any questions today? Any comments?
No, not really.
Can you
Not
go
really.
back for a second?
Oh yes, let me just save. Okay, and there you are. How are you doing with the homework?
I haven't started yet. Gonna start tomorrow, so day after tomorrow we might have some questions for you.
Okay, so no problem. So yeah. So how many problems are there? I don't remember. Are there many problems?
8 problems.
Eight problems. Okay. Okay, not so bad. And remind me, the deadline is?
Friday or Saturday.
Friday or Saturday. So I guess that we're going to have to extend it a bit, right?
No, I think we hope we can manage because then we have other stuff that we need to do. So I think we cannot exceed it anymore.
Okay.
We just try to manage.
Okay.
Yeah, it's and the deadline is Friday, and it's fine. We can do it.
Okay. So, but on Friday you're not going to go out, I guess.
No, we don't go out actually any Friday, so it doesn't matter.
Say it again. So you don't go out any Friday?
Go out on any Friday. It doesn't matter.
Okay. So, okay, it's okay. So, but if at some point you need more time, that's okay with me. Okay, so I can extend it to Monday or Tuesday or some point next week. So no problem with me. Okay, I don't know how the other people are doing. There aren't many people in this class, right?
No, but I think that they have already done the homework.
Oh, really?
I think so,
Or
at least.
they talked about those problems already, like they have started at least.
Okay. So I guess that they are following the videos, right? Okay. Well,
But
that's
yeah,
good.
me and Hilary, we are also taking another, not like a side. We are taking like the both modules of our like mathematics. How to say? We are taking also data analysis besides
economics. Yeah, and that's why we are a bit slower than the other people who take this course, because we have like a few more things to do. So
Okay. So you're taking data analytics?
analysis, I think it's rather analysis, but
Data analysis. Okay, so later on you can tell me what that's about. Okay, one of these days. That sounds interesting. Okay, maybe it's from computer science?
Yeah. It's more like that, yeah. We program there and stuff like that, so.
Okay. All right. Okay, so well, maybe I should stop recording. And